So we have the bunnies versus viruses notes. The bunnies, we start out with 2 bunnies. We have Buddy and Missy, and then they have babies. They have 6 every month. So it follows the pattern of adding 6. And we were able to write our recursive rule as next equals now plus 6. Anytime you're adding, this is creating a linear function. And then anytime, like with the viruses, we started out with 3 little viruses, and then they replicated really fast. It was times 5 every day. And so it increased really rapidly. So we were able to come up with our next equals now times 5. Anytime you're multiplying, then that's an exponential situation. So we did the bunnies notes where we had the arithmetic sequence. This is familiar to us. We've been doing arithmetic sequences where you're looking at how much it's increasing by. And then we did the rule. Started out with 2. Then we had the 2 plus 6 baby bunnies. Then we had 2 plus 6 and then another 6 for the next month. And then we had 2 plus 6 and 6 and then 6 more that month. Anytime that you do repeated addition, then you can change that to a multiplication problem. 6 times whatever n is. So the recursive rule, a sub n is 2 plus 6n. We can also write this as a function. I'm going to write it as a y equals function. So this is a linear situation because you're starting out with 2 and then you're adding 6 every month. So we can write this as our rate. 6 is our rate plus the starting amount. 6x plus 2. So remember 2 is what we started with. And 6 is your rate. So we have the function. So we're going to graph it now. So let's think about this as quadrant 1. So we have the horizontal axis. That is x. Our vertical axis is y. And what does x represent in this situation?
The number of bunnies.
But if we look at this table, what's x? Yeah, months. What is y?
Bunnies.
So x is time in months. So I'm going to put down here just months. Oops. I can't spell months. And then the y is the number of bunnies. So we need to graph this. So I'm going to use my ruler and use the centimeters to make increments. Because what happens if I do these increments off? What if I do just tick marks anywhere I want and they're not equally spaced? Is my graph going to look right?
No.
My graph won't look right. So I've got to make sure they're equally spaced. So that's why I use my ruler. So I'm going to start here. I'm going to go by half centimeters and do little increment marks, little markings. So get out your ruler and do that too. And so we start out at 0 for the origin, and then for months, it's just going by ones. So that's easy to do. And so we'll do the same thing for the y-axis. I'm gonna make sure that my increments are equally spaced. So in order to get as many points as we can, we need to make sure that we set up our counting here. So y goes from 2 to 8 to 14 to 20. So that means I need to be close to 20. So I look here and see, I'm going to have 11.
I went by 2.
Yeah, 2 sound easy. 2, 4, 6, 8, 12, 8, 20, 22. So let's plot our data on here. So 0, 2 is the first one. 0, 2 is basically our y-intercept.
Mm-hmm.
And then 1, 8 to 14. 3, 20. And let's see if we can connect these dots using our ruler. Looks pretty good. This looks pretty familiar.
Yep.
What kind of function is this?
Linear.
Yeah, so it's a linear function. And a linear function, the graph looks like a line.
What does it say?
The linear function.
Graph is line.
Carson.
Okay, so let's move over to the viruses now. Let's write this as a sequence. So we did a sequence here. But the thing is, they're not the same type of sequence because one is being
Added, one's being multiplied.
so it's actually called something new.
Exponential.
It's exponential, but it's called a geometric sequence.
Just have to remember.
You can just put arrows. So we have the geometric sequence, which was 3, 15, 75. What was that third number that we found?
375.
Yeah, 375. And sequences will go on and on. So I'm going to put comma and then 3 dots that represent going on and on. Okay, so we did looking at a sequence. It goes like this. And what operation is happening with that sequence?
Times 5.
Yeah, so times 5. kind of fuzzy for some reason. Okay, so let's do our X, roll, and Y, a table. So on here, the X is 0. And to get our 3 little viruses, that's just what we start with. So put 3, and then Y is 3.
So your Y intercept is 3.
Mm-hmm. Yep, your Y intercept is 3. Exactly. It's your starting amount. All right, so what about if X is 1? What did we do to 3 to get to
It's 3
15?
times 5.
Yeah, it's just 3 times 5.
And then 3 times 5 times 5.
Mm-hmm. And then for our second day, you getting this down?
Yeah.
3 times 5 is what we had before, but then times 5 more. 3 times 5 times 5
Didn't you just
is
do that as
75.
an exponent then?
Yeah, so could we write this as an exponent? Mm-hmm. So this is 3 times 5 times 5, and then times another 5.
It's 3 to the 3rd power.
Yeah, so it's 3. No, it's 3, and then 5 to the how many 5s are there?
Oh, it's 3.
3, yeah.
Let's see.
Oh, 3 times 5 to the 3rd power.
Yeah, so I could do, we'll clear that, 3 times 5 times 5 times 5, or 3 times 5 raised to the 3rd power. They're the same, they're equivalent. So we saw that this was repeated multiplication. Write that down here, repeated mult means, what does that mean? Where we have repeated multiplication.
Exponential.
Exponential.
Yeah. Oh, that was 375. Sorry, forgot that number. Okay, so let's write, what about if we have X days? How can we write a rule if there are X days?
Without the number.
Without which number?
The 3.
The what?
The 3.
Which 3?
Squared.
The exponent. So it's 3 times 5. So we don't know how many times 5 is being multiplied.
So it would either be like.
Yeah. Your variable would be X. So our recursive rule is next equals now times 5. And we can write this as a function, y equals. So you can write a function as f of x equals or y equals. And it's whatever our rule is that we came up here. 3 times 5 to the x.
Wouldn't that mean like it's curved or something like that?
Yeah, we're about to see that right now. All right, so let's create our x and y axis, our graph. So what does x represent?
Days.
Days, yep.
Yeah, it is.
Days. What does y represent? Yeah. Number of viruses. Okay, can I just put numbers here?
No,
What do I need to do?
lines.
Yeah, I need to space it out equally.
think 15 is
I don't know. Okay, what do we need to do? What should I do my days by?
Do by
No,
100.
3.
Days.
1.
Days are going by ones. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, and then what about number of viruses?
25. 50.
If there's 11 and I want to get at least 375,
4.
34. I really don't want to do a number like that.
15.
Huh?
100.
What about 40? 40 will get us to 440. Let's go by 40s.
40.
Yeah. 40, 80. What's next?
120.
Uh-huh. Plus another 40.
160.
Yeah. Plus another 140.
200.
Mm-hmm. Another 40. Another 40. Another 40. Another 40.
I don't know.
I'll start at 3.
Okay, so let's plot 0, 3. Where is that going to be at?
Huh.
3.
Like close to the bottom of the. Yeah, it's going to be like down there. I did it like that. And then what about 115?
1.
Like, just like a little inch, like,
Yeah, less than half. Because half would be 20. 275. Close to 80.
yeah.
Oh.
And then 375. We're going to kind of estimate, you know. Is this straight?
No.
So
it's
what-
curved. Technically.
Exponential.
Nope. Have some more here.
Put a little arrow there.
To keep going.
Because it
Wait,
goes.
won't it eventually just become straight?
No.
Will it actually be straight? Or because straight will mean that they're on the exact same line, like there's no improvement at all. There's no increase.
Never.
It's actually going to keep on going. It's going
gonna
to
go
look
like-
straight.
it's gonna go like,
What were you doing?
Uh-huh.
oh.
So this is more of a curve. So this is called exponential. Exponential function. And so what does the graph look like?
Okay.
Yeah. Okay, so if we compare these to each other, there's lots of similarities, but then quite a few differences. Because if you look here, this is addition. But then here, I forgot to put multiplication. So looking at the table, you can find it being exponential by looking at the table. Table means multiply. What about the graph? What's the difference here between linear and exponential?
It's curved.
It's a curved graph. And then the function. This is very familiar to us. It's 6x plus 2. That's linear. It's like mx plus b. This is something we haven't really seen much of yet. What does 3 represent?
Your y-intercept.
Y-intercept, which is it our start or our rate?
Your start.
Start. So go ahead and put that here. Start. And then what does the 5 represent? What did it represent in our table? What we're multiplying, right?
Yeah.
So that's our constant rate.
Whatever the exponent's gonna be.
Yeah. So multiplicative rate.
It's like the base.
It
was. Yeah.
All right. So go ahead and put this in your journal now.